Okay, circuit protection devices part 4. This I think is probably the longest video in our series so far, so I will try and get through this as quickly as possible in order to not melt your brain with my boring voice. All right, so we left off at phase failure protection for three-phase motors, and we need to move on to phase reversal protection. Right, so if any two-phase conductors in a three-phase supply to a motor are reversed, the motor rotation will be reversed. All right, let's think about that for a second. I mentioned this in the last video that if I reverse two phases, any two phases, doesn't matter, then the motor direction will be reversed. Just as a little additional point on that, if we think about it, if I reverse the direction or reverse any two, swap over any two conductors, then it means that if I swap any two conductors, it'll reverse back again. It doesn't matter. I don't have to switch the original two back. I could just switch any two. Any two. You just go in there and go, I need to reverse the motor. Choose any two, swap them over. Neat, huh? In most cases, machines driven by three-phase motors are unidirectional. That is, they can only be rotated in one direction. That's like the big log milling thing I was talking about before, right? So we don't want that to go backwards and start pushing the logs back up the production line. Hell no. It's essential, therefore, that the phase sequence of a three-phase supply is correct, so the motor can drive the machinery in the correct direction. And if you can't figure that out by context, the phase sequence means the order of the phases. 1, 2, 3. If not, this will cause all three-phase motors within an installation to be reversed with consequential damage to plant and machinery, including the risk of injury to staff. So it's obviously pretty dangerous if things starts going backwards. Like I said in my earlier example about the garage door opener, okay, it's probably not the end of the world. Like, I have to figure out that the buttons are reversed, but that's not going to cause too much drama. But there are almost every other example I could think of. We definitely do not want things running in the opposite direction. Very bad news. So in this one here, we have a phase failure and phase reversal relay. So that is going to stop power to our control circuit, which will kill power to our main contactor if we get a phase reversal. Phases must be maintained in the correct direction. So that's all we're saying about phase reversal. This here says phase reversal, but actually if we read this, it is talking about no voltage protection, which I mentioned earlier. So no voltage protection means when the power goes off, we don't want the machinery to automatically restart when the power comes back on. So when power is re-established, it will not come on again until the start button is pushed. Automatic and unexpected restarting of a motor could cause injury to the operator. Actually, I kind of feel like we're missing a couple of slides because we kind of just skipped past the end of phase reversal and went straight into like the second slide maybe of no voltage protection. Nevertheless, I have already talked about this, so you're lucky. We don't need that slide. As I said earlier, when the power goes off, I do not want my motors to restart automatically. So using a normal direct online starter, so having a start stop button with a coil that needs to be energized to pull in the contactor means that turning the power off is effectively like pushing the stop button. Everything will just sit there until I push the start again, even if the power comes back on. Motors should not be run at lowered supply voltage and full load torque for any length of time. So if our voltage decreases, maybe it doesn't cut off, but if it decreases, that's also going to cause us some problems because it increases the current and it reduces the running speed, which will reduce the cooling effect, because usually the motors are cooled by having a fan on the motor itself, so it's self-cooling. If I reduce the speed, then I reduce the cooling, and the reduction of cooling means that the motor windings may overheat and burn out even when the motor is only drawing normal full load current. So it might be drawing normal current, but if I don't have it running at full speed, then I might lose some of my cooling. but not running at full speed will also increase the current. That's just the thing. If I'm pushing the same load at a lower speed, it's going to draw more current. So we also want low voltage protection, and our DOL starter will give us the same thing, because when the supply drops on that coil, it's going to switch off and it won't switch back on until I push the start button. Mechanical stress. When a motor is used continuously under severe mechanical conditions, it heats up until the temperature exceeds the temperature rating of the stator's insulation. Once this occurs, the windings are irreversibly damaged. Switching of the motor immediately in the event of switching off the motor immediately in the event of excessively high overload or stalling can prevent unnecessary mechanical and thermal stress of the motor and transmission, and reduce the consequences of accidents and lost production. A gradual developing overload, e.g. a bearing failure, can be detected in good time and signaled. The protection function is enabled as soon as the motor has fully started. Okay, so this is talking about a mechanical stress on a motor, and a particular type of overload that could protect us against that. So what we need to be aware of here when it's talking in this first one here, that the insulation melting down. So remember, if you've seen inside a motor, and I'm sure we all have some awareness now, the motor is generally just made up of coiled copper wire. Now, it just looks like coiled copper wire most of the time, but it is actually insulated. It needs to be insulated. Those coils need to be coils, not just a thick bunch of wire. And it's usually just a thin lacquer, so it's transparent, which is why it looks like it's just copper wire there. That insulation will melt when it gets too hot. Once it melts, then there's no insulation, right? So then the copper wires are going to be touching together. We have short circuits within our motor. Everything goes bad. Motor is destroyed at that point. There's a couple of ways that we can protect against this. And generally, what we would do is, I've talked about this before, having a thermistor inside the motor windings is helpful. Because if the motor windings start to get too hot, it's going to open or go to a high resistance and cut supply to the motor. Testing, actually, the maintenance and testing schedule can help you here, right? So the last sentence there is a gradually developing overload, for example, a bearing failure. Well, what does that mean? If my bearing fails, so if you think about the motor, inside the motor, we've got our rotor turning, that's sitting inside a bearing, or there's bearings at each end of the rotor, which enable it to spin. It doesn't just spin in mid-air, and it's certainly not, the rotor shafts are certainly not screwed down hard. They have to be able to spin, so we have bearings. If a bearing fails, like it wears out, all the grease leaks out of it, and you've just got metal on metal, and eventually flies to bits, or just wears down, so it's not doing a particularly good job anymore. In this context, what that means is that we have a high friction inside that bearing. So it's going to make the motor harder to turn, so it's going to cause some sort of mechanical stress on the motor. It's going to cause the motor to work harder. It's going to cause, therefore, higher current. And so an overload, in that case, an overload could operate to protect that, because as the current starts to increase, then the overload's going to trip out. So we may be able to detect that the overload's going to trip, and then we go, well, why is the overload tripping? And we go and have a look, and oh, that bearing is toasted. On the other hand, it may not do that. A testing regime where you go and check the running current of your motors can help you do that, and that's a good part of a good maintenance regime, particularly within some sort of plant operation, a factory or something like that, where we're actually testing regularly the motors, the current being drawn by our motors, because that's going to give us a good indication. If we record that information, and then over time we can see, that motor 4 and 5 are doing the same job, but motor, 6 months ago they were drawing the same current, but gradually month by month, motor 4 is starting to, this is like an extra half an amp every month, and now it's drawing 3 amps more than the other one. Then you're going to go and have a look. We need to see what's going on there. So there's a number of ways that we can identify overloads like that, and developing overloads, something that, obviously with the bearing, it might not fail immediately, but it might get worse and worse over time. And if we can find that and fix it before it flies to bits, that's massively to our advantage, right? Because that means that we can fix it in our own time. When the machine's going to be shut down, scheduled for a shutdown, cool, we'll get in and we'll replace that bearing that's starting to wear out, as opposed to waiting for it to fly to bits and then suddenly everyone's standing around doing nothing while I'm there replacing that bearing. And trust me, that sucks. It's happened way more times than I'd like to admit. Well, actually, it happens nearly every time you get a breakdown. Everyone is standing around waiting for you to fix it. There is nothing worse in the world than everybody in a factory standing over your shoulder watching you work, because they can't do anything until you're finished. Or even worse than that, like in Timor when a switchboard caught fire and everyone's standing there because they can't have any hot food or use any power of any kind, and all the air conditioning is turned off and it's 45 degrees and they're all sitting there waiting for you to finish rebuilding the switchboard. Fun times. What a life, eh? That's back in the olden days when I was allowed out of my house. Okay, so this is a very badly put together slide. Here we go. Poor selection. Okay, so if I select my protection, this is not just motor protection anymore, this is any kind of protection. If I select them badly, what could happen? Well, so here are some of the things that I could do, some of the effects, no, not the effects, some of the causes of failures by poor selection. So I could underrate my protection, overrate my protection, select the incorrect category of duty, incorrect fusing or tripping factor, or the incorrect rupturing capacity. What are each of those likely to do? Let us have a look. Effects of poor selection. Underrated. So underrating means that the protective device is too small for the load current it is to carry. It results in frequent rupturing and mechanical damage to the equipment it is protecting. It'll result in nuisance tripping. Nuisance tripping will be the first thing that we'll see, right? Because if I have a 10 amp circuit breaker on my sockets, then every time I turn the kettle on at the same time as the dishwasher is running, then it trips the circuit breaker. And that's a pain. But we could also get mechanical damage. If it's in a plant or something, every time it trips, then everything shuts down, and that could cause some issues. So we definitely don't want to we don't want our protective device to be too small for the load it's carrying. Overrating our fuse is just as bad, or protective device is just as bad. Probably worse, actually. This is a more common issue. Is the fuse rating is too large to give adequate protection to the circuit, so that results in circuit and damage to the cables connecting to the equipment, because we get overcurrent, current that's too high. So if I've got a cable that's rated for 30 amps and I put a 40 amp fuse on it, then I'm going to run at 40 amps. If I'm running at 40 amps, then the cable is going to start to burn out, but the fuse is going to do nothing. So if we overrate our protection, then we're not protecting the circuit and no longer functions as protection. Incorrect category of duty. Selecting a fuse link that has an incorrect category of duty could result in that link not being able to interrupt a major fault without causing damage to its surroundings. So that's where the fuse, the HRC fuse, and as I said in earlier videos, go and watch the other Canvas videos because they're really good. There's a video, one of them has a clip of a HRC fuse essentially exploding, which is quite fun to see. And that could happen if we have the incorrect category of duty. Incorrect fusing or tripping factor. So a very high tripping factor, the too large tripping factor, may result in the device not operating under overload conditions. So remember, our tripping factor is effectively the difference between our minimum tripping and maximum tripping current. So if that's too high, then we have this very large window of minimum and maximum, which could cause, we could have overloads and they don't get tripped. And if I have it too small, then we have nuisance operation. So that's where if my minimum tripping and maximum tripping current are too close together, let's say I have a 20 amp circuit breaker and my minimum tripping current is 19.9 and my maximum is 20.1. Well, that's a pain, right? Because every now and then I might draw 22 amps for a minute, and it's probably not the end of the world. But if my tripping factor is too low, then every time I hit 20 amps, it's going to trip straight away, which is a nuisance, and we get nuisance tripping. So we need to have a decent tripping factor, but not too high or not too low. Incorrect rupturing capacity. If this is too small under short circuit fault conditions, the device may not safely handle the current and could result in destruction, arcing, or even fire. So remember, our rupturing capacity is how much current that the device can safely protect against or safely break. So if I have a short circuit current of 4,000 amps and my rupturing capacity is 5,000 amps, that's fine. If I have a rupturing capacity of 5,000 amps and my short circuit current is 10,000 amps, then that 10,000 amps, when it happens, it might not even care that the circuit breaker has tripped or that the HRC has blown. It may be enough current to just keep maintaining an arc across the terminals and just continue running, and we have massive arcing and fires and all sorts of crazy stuff. So we definitely don't want our rupturing capacity to be too low. The only way we can determine that, do our earth loop impedance test, work out what our prospective short circuit current is, make sure our rupturing capacity is greater than that. Okay, the summary chart for selecting protective devices. I'll let you guys read that because it's pretty obvious and straightforward. So it's giving us features and uses of different types, rewirable, HRCs, MCBs. So it talks about that there is telling us about what the different uses might be, what are the advantages and disadvantages. Make sure you have a read of it because that's in your test. Speaking of tests, the last number of your access code is 2. Last number of your access code is 2. This is a 4-part video, so you should now have 4 digits for your access code, which means you can go and do your test now, but not before you watch those other videos in Canvas. That's it from me. That's that one out of the way. That was quite a long topic. I feel quite tired now, so I might go and have a nap. As ever, if you're having trouble, get in touch, let me know, and we will work it out. I can tell you so far that the people who are getting in touch, who are getting ahead and getting in touch with me when they're having problems, they are providing an immense help to everybody else, because as soon as I see that one person is struggling with something, I can work through that with them, then I know that I need to talk about that same thing with everybody else. So if you are struggling, don't be shy. It's definitely helpful to the rest of your class when you do that. So thank you to those people. All right, that's it from me for now. I'll see you at the next one. It'll be RCDs, I think. See you, bye.